So we're back, and let us now pay some special attention to the solar wind. We discussed these transonic solutions, and turns out that only solutions of kind 1 and 2 are transonic, right? 1 would be this one and 2 would be this one, right? Okay, so I made a slight mistake when I said this last time. I will rectify it in a minute, but let's now look at the general solution once again, this. And we said that depending upon the constant of integration, you can have any one of these solutions, either solution 1, solution 2, or solution kind of 3 or 4, or for that matter 5 or 6. And we eliminated solutions 5 and 6 because they are not physical. All right, so we really need to worry only about the other kinds of solutions. And of those, only solutions of the kind 1, these, and solutions 2, these, are transonic. They pass smoothly through the sonic point where this represents the square of the Mach number and this represents r, right? So therefore, so let us consider this. This is a little better. This is a slightly larger canvas to talk about, and so let me eliminate. This is r. Okay, only 1 and 2 are transonic. 1 would be this and 2 would be this. Okay, and from the general solution, what would be the values of C for which you would get solutions like 1 and 2? Turns out that for 1 and 2 you have in C equals -3 in here. If you have C equals -3, you will get solutions of the kind 1 and 2. So this is one thing I wanted to mention before proceeding. The other thing I wanted to mention was that I had made a mistake. You see, suppose we are considering the solar wind, right? And so let us now think about what the solar wind means. The solar wind, as I explained maybe a couple of classes earlier, is a wind emanating from the outermost atmosphere of the sun, which is the corona. Okay, and so, and the outermost atmosphere of the sun, it kind of it essentially boils off. Okay, so the gas or the plasma near the corona is almost at rest. I mean, it has a very small velocity, but it's almost at rest. So it's definitely subsonic, right at the surface of the sun, right? And then it goes out, eventually passes through a sonic point where the velocity becomes equal to the speed of sound, and then becomes supersonic. So we, from among 1 and 2, we should choose a solution which is subsonic at small r, and this is the sonic point, Mach number equal to 1. So we should choose a solution that's subsonic at small r, passes through a sonic point, and at large r it becomes supersonic, right? So that would be this solution, this branch 2, right? You see, at small r the Mach number is less than 1, and as r increases it eventually reaches a sonic point. This would be the sonic point, and as r increases even further, the Mach number increases and becomes larger than 1. So this kind of a solution, for which, if I was to redraw the solution, redraw this, r Mach number squared, and this is where it's 1, the kind of solution that looks like this. Okay, so at small r, here Mach number is less than 1, at some here this would be arsonic, and here Mach number is greater than 1, right. So, for larger r the Mach number is greater than 1, and these are solutions of the kind 2, and these represents solutions of the kind 2 represent solutions that are appropriate for the solar wind. I had, when we met last week, I had mistakenly said that solutions of the kind 1 which look like this, which are also transonic, they would be appropriate for the solar wind. But you see, the mistake there is that solutions of the kind 1 which look like this, they are supersonic at small r. That's not what we want. Okay, solutions of the kind 1 would look like this. R, I have one here, right, and I would have something that looks like this. These would be solutions of the kind 1, and this would be the sonic point. Here the Mach number is less than 1, and here the Mach number is greater than 1, clearly. So, what does this represent? What could this represent? This could represent gas that is kind of, at rest at infinity, at very large distances, you see, and it's attracted towards a compact object. It's trying to accrete onto a compact object, and as it's attracted, as it's accreting, the speed increases, and therefore the Mach number increases, right, and it eventually passes through a sonic point, right, and as it accelerates even further, it comes even closer to the star, right, and it becomes quite supersonic. Okay, so it becomes quite supersonic. So solutions of this kind represent spherical accretion. Okay, we just discussed this in some detail, and we said that if we are talking about the solar wind, we really should be talking about solutions like this, solutions like 2, which start out subsonic at small radii, pass through a sonic point, and become supersonic at large distances, right. So, a little bit about the solar wind. This was actually predicted by Eugene Parker back in 1958, simply based on the high temperature of the solar corona. Simply based on this fact, he surmised that there should be a wind that is flowing outwards. Okay, this was the main thing. He figured that the pressure at the base of the million-degree corona is so high that it has to drive it. It drives, or it has to drive it. It has to drive a transonic solar wind. Well, okay, whether the solar wind has to be transonic or not is another matter, but a transonic solar wind was the most elegant solution, solutions of the type 2. Okay, and the actual discovery of the solar wind happened after 1958, in fact. Okay, and I will show you an instance where, it was shown how the observational confirmation of the solar wind was quite interesting, the way it happened. Okay, so but it was among the first few instances where the theoretical prediction predated the observation. Okay, so this is quite a brilliant thing. This doesn't happen very often. Okay, most of the time there is a puzzling observation. and the existing theories, existing sort of existing understanding doesn't fit in. So one has to invent or cook up or whatever a theory that fits the observation. Here you see, this was the observational fact that the solar corona was 1,000,000 degree hot. This was the observational fact, and this was deduced from observations of eclipses. And one of the most important eclipse observations in fact happened in Guntur back in 1940s, if I'm not mistaken, and that's when helium was observed. Helium was discovered. Helium was discovered in the sun first and then on the earth, interestingly enough. Okay, so I would urge you to Google discovery of helium. If you Google this, you'll find several interesting pieces of information, and you'll also find out that helium was discovered using data from a solar eclipse that was observed at Guntur in Andhra Pradesh in India, okay, by a French astronomer called Jules Janssen, if I'm not mistaken. And so now, why am I saying this? This is because the discovery of helium was one of the most important pieces in confirming that the solar corona is actually 1,000,000 degrees hot. Well, it was suspected to be 1,000,000 degrees hot earlier also, but that particular line that they observed was thought to be coming from entirely new element that they call coronium. Okay, it was only with this discovery that it was realized that it was actually an element that was already kind of known. And so the fact that the solar corona was 1,000,000 degree hot was realized soon after the discovery of helium. Now what Parker did was he figured that if the corona is 1,000,000 degree hot, then the pressure is so high that the pressure in the corona, the pressure right there is so high that it cannot be, the corona cannot be held back. The outer atmosphere cannot be held back by the gravity of the sun. It has to expand and flow outwards in a manner of reminiscent of solution 2 that we have just discussed. Okay, and this is among the few instances where the theoretical prediction predated the observation. Turns out that this idea was so radical that it was thought to be wrong, and Parker's seminal paper was actually rejected by the referee. Okay, and it was only after a lot of give and take and that Parker finally managed to have his paper accepted. And sure enough, a few years later, the accuracy of the validity of his prediction was proved outstandingly right, and the solar wind was indeed observationally confirmed. Okay, so this is quite a remarkable story. In a sense, we are all immersed in the solar wind. You see, the solar wind is something that emanates from the sun and it flows outwards. Okay, and it flows outwards and goes on, keeps going on up until it hits up until I think beyond the orbit of Neptune or even beyond Pluto. Okay, and it continues on until the ram pressure of the solar wind cannot take it any further. Okay, the pressure of the surrounding interstellar medium is so large that it acts as a wall, and in some sense it blocks the solar wind. Okay, and that place is called the heliopause. Okay, and in some sense the solar system is thought to be that volume which is permeated by the solar wind. Okay, up until the heliopause, people think of that as the solar system. So we are of course well within the heliopause. So we are also immersed in the solar wind as we speak. We are immersed in the solar wind from the sun, which is a stream of highly charged particles, hot particles. It's streaming past us, it's streaming past the earth as we speak. We are immersed in the solar wind. The only thing is, of course, the charged particles do not enter the earth's atmosphere. Okay, the earth has its magnetic field, and the magnetic field protects the atmosphere from the charged particles entering it. That's because, if you have a magnetic field like so, and magnetic field pointing this way, and you have a charged particle, it is caught in the magnetic field. It exhibits, it it rotates. Okay, it exhibits circular motion, and if it also has a component of velocity that's parallel to the magnetic field, the motion becomes helical like this. Okay, so a charged particle that is seeking to enter like this cannot come in, it gets caught in the magnetic field. Of course, how well it gets caught, in other words, how large is the radius of gyration like this, or is the radius of gyration like this, that depends upon the strength of the magnetic field, that depends upon the combination, that depends upon two things, that depends upon the strength of the magnetic field and the energy of the charged particle. So if the Earth was somewhere here, and this would be the geomagnetic field, which sort of is a dipole like this, the Earth is something like this, and the geomagnetic field is a dipole. Okay, so this would be the North Pole and this would be the South Pole. If you're standing at the equator, it looks somewhat like this. There's a kind of so a charged particle coming in like this gets caught, and it gyrates along the magnetic field. Whereas if a charged particle is coming like this towards the poles, it has relatively easy access. Okay, I'm saying all this simply to explain this statement, simply to explain this particular statement, that we are all immersed in the solar wind. Okay, in other words, we standing here on the Earth, we are all immersed in the solar wind. The solar wind is blowing past the Earth all the way, and it goes this way. Okay, and the Earth kind of presents a bit of an obstacle to the solar wind, but that's okay. The solar wind has so much ram pressure that it really doesn't care. It blows right past the Earth and goes on beyond the orbit of Pluto, okay, until it hits the heliopause. Okay, so this is the thing, and so this is an interesting observation. It kind of tells you how the solar wind was discovered. You see, this is where the sun is. So the sun is towards here. Okay, the sun is somewhere here, and this would represent a comet that is blowing past like this. Sorry, the sun is somewhere here, and these arrows point in the direction of the purported solar wind. Okay, so here's a comet that's going this way, and I'm sure you know about comets. Comets are objects from the Kuiper belt that often they're very solar system objects, and several of them pass through our field of view every year. And this would be a typical comet, and it turns out that it has two kinds of tails. Okay, it has what's called a dust tail, and these would be essentially uncharged particles. Okay, and this would be a gas tail, which comprises of somewhat of charged particles, not all, but some of them. And the remarkable observation was that the gas tails always pointed away from the sun. The gas tails always point away from the sun, somewhat like a kite. Okay, so you remember when you fly kites and you have the tail of your kite? The tail of your kite always points, always blows in the wind like this. Okay, the tail of your kite is as an indicator of the wind direction. If the wind is blowing like this, the tail of the kite will be pointing along the wind, and that's exactly what gas tails seem to do. Okay, they're always pointing away from the sun. It's almost as though there's a wind blowing away from the sun, okay, and that is influencing the tail of the comet. This would be the comet, and that's influencing the tail of the comet. More specifically, that's influencing the tail of the comet, which comprises charged particles. That's because, although we have not talked about magnetic fields at all so far, Turns out that the solar wind also carries, essentially combs out the intrinsic magnetic field of the sun, okay, and it combs it out into a pattern. Okay, and so what these charged particles are actually doing are they are following the large scale magnetic field from the sun, which is drawn out by the solar wind. So the solar wind is essential to this description. Okay, the fact that the charged particles are following the magnetic field, which is drawn out by the solar wind, that's a secondary. It's an important effect, but that's a secondary effect. So in some sense, this was one of the first proofs of the existence of a solar wind. Okay, all right. So this is one thing, but I don't want to leave you with an impression that the solar wind problem is completely solved. Far from it, actually. Okay, there are a few other complications to the solar wind problem. It's like this: the solar wind is not spherically symmetric. Okay, although our solution which we just described is a spherically symmetric solution, to zeroth order it's a very good description. That's the main thing I want to convey here. What's more, it involves magnetic fields, which we did not discuss at all. In other words, the solar wind is magnetized. It's a magnetized fluid, which we did not discuss at all. Okay, so this is another thing, and what's more, the solar wind continually accelerates. In other words, there is a requirement for extended heating. In other words, you remember our description, what it does is it takes the description of the solar wind, which looks like this. It takes a hot plasma at the base of the corona and it passes it through the sonic point, and as it moves out, obviously it's getting cooler. That's why it's getting accelerated. The internal energy of the plasma is being converted into the kinetic energy, the bulk kinetic energy of the solar wind, and that's why the bulk kinetic energy of the solar wind is increasing, and the Mach number becomes larger than 1, and that's fine. Now it turns out that observations are pointing out that it's actually accelerating more than what this curve would predict. In other words, there is a requirement for extended heating even as the solar wind flows out. Okay, and this is not accounted for in our simple-minded solutions. So these 3 points are just to give you an understanding, but the problem is not really solved yet. There are several other interesting features. While the basics of the problem are well laid out by these simple solutions, the details and some very important details are far from clear. Now let me show you one interesting observation which has to do with this point, the fact that the solar wind is not spherically symmetric, and that is given by this picture. What this is, there was a spacecraft called Ulysses, Ulysses out here, and this particular SWOOPS is an instrument about Ulysses, and this is a pretty old spacecraft. If you Google Ulysses, you'll find out when it flew, and what the spacecraft did was it took a pass over the sun all the way from the poles, from the South Pole to the equator to the North Pole and back. Okay, and these are actual observations. These are observations of the sun taken with these are observations which are superimposed. Okay, these are observations of the sun taken with the extreme ultraviolet imaging telescope aboard the SOHO spacecraft, and these are observations of the extended solar corona superposed. It's not this and this do not come from the same instrument. They're superposed here for visual clarity. Okay, and so this is essentially the solar corona, the inner solar corona, and these comprise streamers and everything. But these are slightly, this is for context, okay? This one and this one are for context. What we are really interested in are these lines. Now, what are these lines? These are measurements of solar wind velocity. Okay, so you have 1000 here and 500 here. So what this is saying is that around the equator, you see this is the equator of the sun, and around the equator the solar wind velocity is around, you see this 500 is here, so this 500 would be somewhere here also. Okay, so around the equator the velocity of the solar wind is around 500 kilometers per second, something like that, around the equator, here, here, also here. Here turns out that it's even lower. 500 would be somewhere here, for instance, and it's around 500. Okay, however, around the poles, you see 1000 is here, and so this would be something like 800 or so, 800, 900, something like that. So around the poles, you see, right exactly at the pole data is missing, but around the poles, you see, the solar wind velocity is much higher. It's around 800 to 900 kilometers per second, whereas around the equator the solar wind velocity is lower. Okay, so therefore the message to take away from this is that the solar wind is bimodal. There is a fast around, I don't know, 7 to 800 kilometers per second over the poles, and slow, meaning around 3 to 400 near equator. This is the message that this figure is telling you. Okay, so clearly this is not a spherically symmetric solar wind. No, a spherically symmetric solar wind would have the same speed irrespective of the equator and the pole, right? So clearly this is not a spherically symmetric solar wind. So this is, you could say, a drawback of the theory that we just outlined. And what is causing this bimodality? Well, roughly speaking, the bimodality is, I would really say, probably not quite clear, caused by the sun's large scale magnetic field. And these are issues that we will, large scale magnetic field. So what we will do is we will take this up, we will take things like magnetic fields and everything a little later, and when we start incorporating magnetic fields into our equation and start discussing the field of magnetohydrodynamics. So we will stop our discussion of the solar wind here, and we will take up a little more about spherical accretion, and thereon start to discuss disk-like accretion next. So we'll stop here for now. Thank you.